Okay, let's do a little calculus. In the notes, we had example 2, very similar to this problem right here. And there's one in the homework, so let's do this one together as a little more practice. The directions say use these summation formulas to rewrite the expression without the summation notation. Use the result to find the sums for n is 10, 100, 1,000, and 10,000. So I'm going to hide this up here. And here is our starting expression. All right. The thing I like to do first, any n's that we already have that are multiplied, we're going to pull them out in front of the summation symbol. So now we have 1 over n cubed, and then we have our summation. And then to the right of the summation, I'm going to distribute the 6k. So we distribute there, and we get 6k squared minus 6k. All right, now we are going to distribute the 1 over n cubed and the summation to the first term, and then again to the second term. So I've got 1 over n cubed, summation of 6k squared, minus, again, we distribute the 1 over n cubed and the summation, and here we just have 6k. Okay. Now that we've got the summation distributed in each term, if we can take any more things to the left of the summation, we'll do that now. So we got a 6 times k squared here. I can move that 6 up here in the numerator. And in our second summation, we do have a 6 times k. I can bring the 6 up here in the numerator. There we go. So now we've got a summation of k squared. Let me use a different color. We have a summation of k squared. We have a formula for that. And we have a summation of k. We also have a formula for that. So in our first term, we have 6 over n cubed. And now the summation of k squared, we can replace with n times n plus 1 times 2n plus 1. And that's all over 6. And then minus, we got our second term. 6 over n cubed, back there. And the summation of k, we have the formula n times n plus 1 over 2. So what we want to do is simplify these down, cancel anything we can. We might have to FOIL a little bit, and we want to condense this down to a single expression. So let's look for those cancellations first. These 6's will divide out to be 1's. This n will knock this n down a power. Now that's n squared. Same thing on our second term. We can divide by 2 here, and 6 divided by 2, that's now a 3. We can cancel this n, and that will knock this down 1 power. So let's keep it 2 separate terms for now. Here's the minus sign in the middle. And on the left, we've got an n squared as our denominator. This canceled down to a 1. So this is n squared. And if I FOIL out the n plus 1 and the 2n plus 1, I get 2n squared plus 3n plus 1. And then after the minus sign here, our denominator again, we had this 2 cancel down to a 1. So the denominator here is also n squared. And now I'm going to distribute the 3 to the n plus 1. So we have 3n plus 3. Notice I grouped that, and we have the negative out here. I could have distributed a negative 3 all at once, but I saved that negative for its own step. Because what we're about to do now is get a common denominator, which we kind of already have. We're going to distribute that negative. So we've got a division line. N squared is our denominator. And here is our 2n squared plus 3n plus 1. Now we distribute the negative, so we get minus 3n minus 3. And in that numerator, there are a couple of terms we can combine. Positive 3n and negative 3n will cancel. The positive 1 and the negative 3 will combine. So now we've got 2n squared minus 2 over n squared. In the WebAssign problem, based on this, that will go in the first box. They want our simplified expression. And now we would put that in our TI-89 calculator and go to the table. And when n is 10, our calculator spits out 1.98. When n goes up to 100, it's 1.9998. When we plug in 1,000, we now get 1.49s, 1, 2, 3, 4 nines, and an 8. And then our biggest number is n is 10,000. And that gives out a decimal 1 point. Now we have 7 number 9s. 1, 2, 3, 4, 5, 6, 7 nines with an 8 at the end. We can see that as our n gets bigger, this number looks like it's approaching 2. If we go back to when we did limits at infinity and we look at this simplified expression here, if we let n go to infinity, the power struggle between the numerator and denominator is a tie. So these would cancel, and that limit at infinity would be 2. Okay, and let's look at this problem here, number 33 out of the old textbook. Use upper and lower sums to approximate the area with a given number of subintervals, a given number of rectangles. So our function here is just the root of x. We start at the origin, and it opens up like a fell-over parabola, and we have the root of 1 is 1. And if we look at the picture, we have 1, 2, 3, 4 rectangles. So the first thing I like to find is our delta x. That is our base of each rectangle, b minus a, divided by n, the number of rectangles. Well, b is 1, and a is 0. So that's going to be 1 minus 0, or 1. And we have 4 rectangles, so n is 4. And that allows us to fill in here on the x-axis. We've got 0. This here is 1/4. And I'm going to not reduce my fractions. I'm going to leave this as 2/4. And then this point right here would be 3/4. And we can replace 1 with 4/4. And you'll see why I like to do that here as the problem progresses. So again, our function is root x. We've got 4 rectangles. The area of one rectangle is base times height. Now we are going to have 4, so this will be base times height 1, plus base times height 2, plus base times height 3, plus base times height 4. Now in each of these, all of the bases are the same. Each base is 1/4. So we can factor the base out, and then we're just going to have a sum of 4 heights. Each of these heights is a product of the function. So when I put in this endpoint and I use the function to go up, that'll hit this point on the function. That will be a height of one of our rectangles. That means that we're going to replace h sub 1 with the square root of an endpoint. Same for h2 and h3 and h4. Now I'm going to do a little color coding on the picture. I'm going to use red dots for the left endpoints. So these 3 red dots give me the left endpoints of rectangles 1, 2, 3, 4. And I guess I can erase this. So the base that we factored out is 1/4. And then we're going to have a sum of 4 heights, the 4 left endpoints. And again, our function is the root. So our first height is going to be the root of 0. That's the red dot here, the left endpoint of rectangle 1. Plus the root of 1/4. That's the left endpoint of rectangle number 2. And then plus the root of 3/4. I forgot 2/4. That should be 2/4. Plus the root of 3/4. So there are my 4 endpoints for the left endpoints of my 4 rectangles. So we've got our 4th out here. Notice under all the radicals we have a root 4 as our denominator, so that will simplify down to just a 2. And then I can leave off the root of 0. The root of 1 here is just 1. plus the root of 2 plus the root of 3. So what I would do is multiply the 4 by 2, and I get an 8 down here. And then you can pull this off with a basic calculator. 1 plus root 2 plus root 3, all divided by 8. I'm going to write it up here in the upper right corner. That's 0.518 square units. That would be the lower sum. That would be our left endpoints. And I'm going to erase this, but leave this work up on top. Throw that in the garbage. All right. So now we can do the same process, but with the right endpoints. So now I'm going to go back to my picture and use blue. Number 1's right endpoint is number 2's old left endpoint, 1/4. And then my second rectangle's right endpoint is 2/4, and then 3/4, and then 4/4. So with the overlap in the middle, I just have to remove this root of 0 and replace it with the root of 4/4. So now I'm going to have my 1/4. And now my 4 heights are the root 1/4 plus root 2/4 plus root 3/4 plus, I needed a little more room. There we go. The root of 4/4. Okay, so we've got, I'm just going to work my way back up here. The 1/4 will distribute at the end. Again, all the denominators are root 4's, so those are all going to just turn into 2's. And then in my numerator, the root of 1 is 1. And then I'll have a root 2 plus a root 3. And the root of 4 here is 2. Once again, to make the calculator work easier, I would multiply the 4 here in the denominator and turn that into an 8. And then I would add my numerators. 1 plus root 2 plus root 3 plus 2, all divided by 8, gives me 0.768. That's my right endpoint sum, or upper sum, my overestimate. So underestimate 0.518, overestimate 0.768. The true value of the area under the curve would lie somewhere in between. Okay, let's do one more odd problem in this video. Number 49 here. In the directions, it says use the limit process, find the area of the region bounded by the graph. So it doesn't limit our number of rectangles. We want the actual area under the curve, not an estimate. So we will let n go to infinity at the end of the problem. So let's come up with an idea here what this graph looks like. We're going from 0 to 1 on the x-axis. X squared plus 2 is a parabola with a y-intercept here of 2, and then it's going to go up. If I plug a 1 into this, I would get 1 squared plus 2, that's 3. That's the height this will ever go. And there's our little sketch of that area, and here will be a representative rectangle. So first thing, let's find our delta x. That is b minus a divided by n number of rectangles. So we're going to go 1 minus 0 is 1. And since we're going to use the limit process, we will leave that as an n until the end of the problem. And we will let n go to infinity. So I can move this, over here. Okay, and they didn't tell us what endpoints to use, right or left. Right endpoints 99 times out of 100 are easier. So our right endpoint formula is going to be our delta x, 1 over n times I. So it's going to be I over n. And I try real hard not to make my i's look like ones. I give them a little squiggle at the end and make sure I dot that I really well. So that means if I do this in the notation in the book, we're going to have a summation from I equals the first rectangle to the nth. We will have f of our right endpoints. That's when we put the right endpoints into the function to get the height. So this is the height of any given rectangle. And then the width of our rectangle is our base, 1 over n. And I guess I can clear a little more room here. So I'm going to sort of squeeze this down here. And now let's jump into the actual function. So we're going to have our summation from I equals 1 to n. Our function is x squared plus 2. So we're going to have x squared plus 2. That's our function. Again, this will determine the height of the rectangles. And our base will be 1 over n. Now what we put into our function here is our right endpoint formula, I over n. I over n. Okay. So the 1 over n I wrote in red. Let's drag that out in front of the summation symbol. And now I'm going to square the I over n. So we square the numerator and get I squared. Our denominator squared is n squared. Let me fix that. And then we've got plus 2. All right, we are going to now distribute the 1 over n and the summation to both of these terms. Let me shrink that up a little bit. There we go. So 1 over n summation to the first term, I squared over n squared, plus 1 over n summation to the constant 2. Now in each of these, again, if we can drag anything else out in front of the summation, that'd be great. So this denominator n squared I can pull out here and multiply with the 1 over n. Now it's 1 over n cubed, and we have a summation of I squared, and we have a formula for that. And this, for right now, I'm just going to leave it alone, 1 over n. We have our summation. I am going to put the n up top here where it should be, and our constant 2 goes right here. So now I am ready to apply our summation formulas. So the 1 over n cubed is going to stay here, but the summation of I squared is n times n plus 1 times 2n plus 1 all over 6. And then in our second summation, we have 1 over n here. And remember, the rule is when we're summing a constant, we just multiply the upper bound by that constant. So that becomes 2n, and I'm going to put a 1 under it. All right, now we got to simplify each of these terms. We don't necessarily have to combine them into a single term. We could, but it's a little extra work, and it doesn't add much to the end. So here we can cancel this n, and this is going to get knocked down a power. Now it's squared. So our first term is going to have a denominator of 6n squared. And if I FOIL out what remains in the numerator, that's going to be 2n squared plus 3n plus 1. And that first term is done. And now in the second term, we're just going to have these n's cancel. So we're left with just 2. So we are ready now to let our n's go to infinity. We're going to apply the limit and let n, our number of rectangles, approach infinity. So in this red fraction, remember back to limits at infinity, we have what I call the power struggle between the numerator and the denominator, and it's a tie. So that 2 divided by 6 is our fraction 1/3. And if we add 2 to that, we get 2n 1/3. And let's turn that into an improper. 7/3 would be our area under the curve. So I hope doing these odd problems together are going to help you out. Ooh, and I should have noted that these, the problem we just did, I believe that helps on WebAssigns 6 and 7. And the previous 2 problems helped on some other ones. I think WebAssign number 5, somewhere around there. So I will see you in class.